We have so far in our study of digital signal processing systems assumed that all of the computations were carried out using real-valued numbers. So we assumed, for instance, in our implementation of digital filters that there was real-valued numbers that were being multiplied and added together in order to implement the given transfer function of the filter. And we also assumed in our study of time-discrete signals that even though the signals were discrete in time, each of the signal samples could take an arbitrary value in the real numbers. However, that's a problem if you want to implement something in practice, because a digital computer or a digital circuit cannot store arbitrary real-valued numbers. So what has to be done is that these real-valued numbers have to be mapped to some finite representation of the real numbers, and that will introduce quantization effects. And this is what we will study in this and the next video. The basic component when considering quantization would be the quantizer Q here, which takes an arbitrary input signal x of n and produces an output signal x hat of n in this case, where each of the values in x hat of n belongs to one of a finite set of possible values of the quantizer. So in this particular example, we've shown a uniform quantizer where the distance between any two such levels is constant. And this is the most typical case, but it's not necessarily the case for all quantizers. So the signal x hat of n may be viewed as a finite level representation of the signal x of n here. And if we label these finite set of levels with binary labels, we could store them in a digital computer and use these values for computations in the implementation of our digital circuit. From a functional point of view, we could view the quantizer as simply a mapping according to such a stair-shape form, whereas input signal values x of n are mapped in steps. So all the values in this range will be mapped to one level, 0. All the signal values in this level will be mapped to the first positive level, and so on for the negative levels. So we could express the error that is made in quantization, or the round-off effect, by looking at the difference between the quantized output and the input, and this is generally what we refer to as the quantization error. So any given quantizer, if you want to map the general input to an arbitrary set of finite levels, it has to taper off somewhere. So there will be a range or a point at which the quantizer saturates and gives the same output value. And this is a necessity if we wish to provide only a finite set of outputs. But within that range of the quantizer, we have the stair-shape form, and the error is given by the similar sawtooth shape within the range of the quantizer. So the range of the quantizer, here denoted R, is one of the important characteristics characterizing a uniform quantizer or a quantizer in general. Another important quantity is the resolution of the quantizer, here denoted delta. So delta is the step size between different steps of the quantizers. So one can think of this as the set of values x of n which are mapped to the same level, or simply the distance from each level to the next. And one can see that the error of the quantizer in a uniform quantizer will always be bounded between delta half and minus delta half within the range of the quantizer. Understanding what a quantizer does, in some sense it's easy because it's a simple staircase function, but working with it mathematically becomes complicated because it's highly nonlinear. So for many types of system analysis, we need a simplified model for what happens in quantization. So the way that this is typically set up is to assume that you have a quantizer with an input and a given output. But then when you want to analyze the effect of quantization, you exchange that with a model which simply has an additive error here. Right? And if the error is given as in the previous slide, this is in fact an exact model, but the complicating factor now is that x of n and e of n, the error, are highly dependent upon each other. However, the modeling assumption comes in when we assume that the error made by the quantizer is independent of the input signal, and that makes it tractable to analysis. So, in the typical additive noise model for quantization, we have, as stated before, the quantizer with an input x of n and an output x hat of n, and we have this model where we make the assumption that the quantization noise is independent of the input signal. And in many cases, that is a reasonable assumption for analysis, even though the assumption on the face of it is completely wrong, because E of n for a true quantizer is deterministically given by the input samples. But however, when we make this modeling assumption with the additive uncorrelated noise, we will typically assume that the additive noise is a white stochastic process, meaning that it has an autocorrelation given by some variance sigma e times a delta function. So it's uncorrelated over time. And we'll, as noted before, assume that the noise here is independent of the input, and this makes it tractable for analysis. We'll also assume that the noise is uniformly distributed over the range of minus delta half to delta half, and this is the range of the quantization error that we saw before within the range of the quantizer. So that's a valid assumption, or a reasonable assumption, if the input signal x of n stays within the range of the quantizer, and we'll motivate this more in what follows. So we can look at this model in the example that we saw previously, where we had the signal x of n which was quantized into x hat of n. So if we, instead of looking at x hat of n, look at the error signal, which is the difference between the output of the quantizer and the input, we get the following signal. So as you can see, of course, if x of n, which in this case is bounded within the range of the quantizer, is mapped to the error here, the error will be bounded in the range delta half to minus delta half. And it's very hard here to see the relation between the error signal and the original input signal. So in general, if you have an input signal that is sufficiently rich in terms of its spectral content so that it's relatively hard to predict, then whatever error signal that you get out will look uncorrelated, or will be largely uncorrelated with the input signal. So that does not necessarily mean that it's independent of the input signal. So it's not, since it's given deterministically. But for the purpose of analysis, assuming that the error signal is independent of the input signal due to the fact that we have low correlation between the error signal and the input signal, is typically an adequate modeling assumption for the analysis that we will carry out. In terms of the uniform assumption over the quantization range, we can do the following argument. So if we have an input signal x of n where each sample is drawn according to some distribution, so this is just a particular example of a probability density over the range -1 to 1, where we apply our quantizer. And our quantizer divides the inputs into a set of ranges defined by the resolution of the quantizer delta, which are then mapped to the center point of these in terms of the quantizer. If we now look at the error, say that we fall within this range, so our signal sample fall within this range. If we look at the quantization error, if we quantize all the values in this range to the center point, we could get the PDF of the quantization error by simply translating this part of the PDF of the original input to the 0 point of the quantizer. But if we look over all different bins of the quantizer, not caring for the error, which bin we happen to fall in, the PDF of the error is given by simply summing up shifted version of the original PDF, where all these shifted versions are shifted to 0 before the addition. So then we get a distribution in the range minus delta half and delta half. And since if we add many of these, they typically tend to add up to something which is largely uniform. And this effect is even strengthened if we move to closer quantization bins, so if we decrease the resolution of the quantizer, or increase the resolution, so we decrease the value of delta. Then we get narrower bins, and the original PDF is more or less constant across these bins if the bins are sufficiently close. And adding up many roughly constant parts will add up to a constant PDF for the noise PDF. We have argued that the noise should be uniformly distributed over this range minus delta half to delta half. But we haven't yet specified what the power of the noise should be. However, the power of the noise follows from the uniform distribution. But the question is, what should it then be? Should it be equal to delta squared? Or should the power of the noise be equal to delta squared over 4? Or should it be delta squared over 12? Or delta squared over 24? The correct answer is option number 3. It should be delta squared over 12. And that can be obtained by simply taking the expectation of the noise squared, which involves the squared noise and the PDF of the noise, which we previously concluded should be uniform between minus delta half and delta half. And if it's uniform over minus delta half to delta half, it has to have a magnitude of 1 over delta, since this is the size of the range. And then just integrating this out gives us the correct answer, delta squared over 12. In a digital system, numbers are stored in a given format for that particular system. And the number format that we choose also in some sense determine the quantization levels or the quantized levels of signals that we can consider within the system. So common to all number formats in a digital system is that they contain a finite number of digits that are somehow stored in the system. But there are two large classes. So one is the floating point formats and one is the fixed point formats. So in a floating point format, essentially what is done is that we have a fixed number of digits that we can use to describe our numbers, but then we have a set of digits which describe where the decimal or the binary comma in a digital system is. So we could move this around, and that gives us much larger flexibility in the magnitude of different numbers that we can store. So in a floating point system, if we can move the point around, we could for instance move it here and have numbers in the million, or we could move it here or here and have numbers which are less than 1 in magnitude, and that's a very large dynamic range. One of the most common floating point formats is the so-called IEEE 754 formats, and this is typically what you get if you program in C, for instance, and you use the double and the single point precision formats on most computing platforms. So this is very good for scientific computing because you get a very large dynamic range. However, the quantized levels that you get if you allow it to move around the comma here would not be uniformly spaced over the real numbers. So there are two drawbacks with that. One is that it's slightly harder to analyze, which is not a real drawback of using this number formats. It only limits our ability to analyze what happens. However, typically if you allow floating point formats, more logic is also required in the computations, which makes the hardware more costly. So the other option is the so-called fixed point number formats. And in those formats, you decide a priori where you want your comma, your decimal comma, or your binary comma if you work with binary numbers, which you would in a typical digital system. So that is fixed. And what that does is that it gives you uniform quantization of the real values. And it's very good for fast computation. And it's typically not as heavy on the hardware that has to be involved in order to implement that. And there are several different ways of representing fixed format numbers as well. And these include the so-called signed magnitude representation. There's something called the ones complement and the twos complement. So the ones and two complements are chosen so that they allow even more efficient implementation of the computational circuits. However, the signed magnitude representation is somewhat easier to understand and to analyze, and this is the one that we will look at in more detail in what follows. In the b plus 1 bit signed magnitude representation, you have b plus 1 bits, b0 to bb, where b0 represent the sign of your number and b1 to bb represent the magnitude of your number. And each b here is simply a binary digit, so it takes a value of either 0 and 1. And you can recreate the numbers from these bits. So if you assume that x belongs to the range of -1 to 1/2, so we assume signals which are within this finite range, or equivalently we choose this as the range of our quantizer, then each x is given by -1 to the b0. So this just sets the sign to be equal to plus if b0 is equal to 0, and -1 minus if b0 is equal to 1. And then the remaining bits here represent the magnitude as powers of 2 to the -I, where I is the index of the particular bit. And this is just a compact way of writing the following, that in binary representation, a signal x is given simply by the plus or the minus, depending on the sign bit, of 0 point, and then the binary representation or the binary expansion of that number using those bits. So to take an example, if we have b equal to 2, so we have 3-bit representation. The first bit represents the sign, so it represents if we're at negative values or at positive values, and the two remaining bits represent the magnitude. So the different magnitudes that we can allow with only 2 bits for the magnitude is 0, 1/4, 1/2, and 3/4. And here we see an inefficiency of the signed magnitude number in that we had two different representations in terms of the bits for the level 0. So that's slightly inefficient and is one of the reasons that many of the actual systems that are involved use ones and two complements instead in order to get around this. But we see that we get a uniform quantizer and we get different levels for the different values between this -1 and 1. Now a question on that. So if we return to this example and we see that in the case when we have 2 bits, we get a resolution of the quantizer given by delta equal to 1/4, which is the distance between the dividing lines determining where we quantize our value, or equivalently the distance between any two numbers on the real line that we can represent. So in the general case, if we have b plus 1 bit signed magnitude representation, what would be the general formula for the quantizer resolution delta in this case? So would it be 1 over 2b, or equivalently 1/2 of b inverse? Or would it be 1 over b squared? Or would it be 1 over 2 to the power of b, or 2 to the minus b? Well, the correct answer is option number 3. It would be 2 to the minus b. And the way to see that is simply to use the fact that the quantizer level is equivalent to the distance between any two numbers that we can represent. So the closest numbers that we can find in this representation are simply numbers which differ only in the last digit. And if we look at the weight of this digit that it has in the representation, it's 2 to the minus b. And this is what gives us the quantizer resolution for a signed magnitude b plus 1 bit quantization of numbers within the range -1 to 1. It also gives us the corresponding quantization noise power when we apply these numbers as approximations of the real numbers that we wish to do calculations on. So since we have the delta value given in the terms of the number of bits, and we know what the quantization noise is, namely delta squared over 12, we can arrive at a similar formula for expressing the corresponding noise power in our additive noise modeling based on the number of bits that we use in our representation. So to summarize, so if we want to do digital computations, we require quantization of the real numbers. And this is simply because we cannot represent and store arbitrary real values in a digital system. So we need to represent the set of real numbers by a finite set of levels. And this is what we do, as in essence, using a number format. So many times we use a fixed point number format for computational efficiency. And the way that we typically analyze quantization in such a system would be through an additive noise model, and we will see examples of that later on. One of the formats that we will look at in the course explicitly is the b plus 1 signed bit magnitude representation, and that can be used to represent numbers in the range -1 to 1. It can be used to represent numbers in any other range as well, but without loss of generality we can assume that our numbers are within the range -1 to 1. And we get a corresponding quantization noise power equal to 2 to the -2b over 12 for this particular representation of numbers.